topics that I usually don't have time to get into. Rocket science on page 52 and the center of mass frame on page 53. Whoops. All right, let me stop that. So if you're curious about the equations for momentum when an object's mass is changing, that's problem 9.49, the rocket propulsion, and you can read that and learn about it. There's some extra tricky questions on there. Great. Also, if you're a physics major, it turns out in modern physics, a lot of times we use what's called the center of mass reference frame. So up until now, we've talked about either, if you remember when we did relative velocity, we talked about either being at the earth frame or with the plane or with the water or whatever. There's also another reference frame you could use, which is the center mass frame. Physicists should read page 53. That said, we're moving on to rotational kinematics, page 55. All right. And so if you open up page 55, there's a lot. That's basically the summary of rotational kinematics. Let me get some markers going here. So that's a lot. So up until now, we've kind of glossed over a lot of different things here. So first off, I want to talk about theta. And we're going to call this angular position. And you can see that right now, I'm writing this as a vector. That is technically wrong. You cannot write an angle as a vector for reasons I will explain in a minute. But in certain special cases, we can treat it as a vector. We're going to restrict ourselves for this class to the cases where theta can be treated as a vector. And let me just say why right now to get it out of the way. Vectors should obey vector addition. Vector addition should be commutative. Meaning if you say vector 1 plus vector 2, the answer should be the same as vector 2 plus vector 1. And I think all of you agree with that, right? It turns out angular vectors don't obey that relationship of commutativity. Okay, depending when you start rotating things, if you rotate x, y, then z, that's going to be different than z, y, then x. So that said, I'm going to just say it like this. We can treat as vector if only rotating about a single axis. And that's what we're going to do. So in that case, we can treat it as a vector. Dom, is there anything more you want to say about that? Because you'd probably go into that in your classes a little bit, right?
Yeah, you got to be careful.
Yeah, so exactly. So like before we had an x vector, right? And a lot of people say x goes to theta. And we'll talk about this analogy in another chapter after we learn about torque, but and angular momentum. But for now, it's not a perfect analogy to say thetas can be treated as vectors. All right. Notice. Pretty important here. We're going to use radians as the default. So already I could tell you something you got to watch out for on test day. Your calculator mode. You know what I'm talking about? Sometimes one class will be in degrees and the other will be in radians. So you have to be just very diligent about constantly checking your calculator, what mode you're in, and be thinking about degrees and radians all the time for the rest of your life. Good? Okay. All right. Now, if we assume that theta is a vector for this one axis of rotation type problem, then the rest of everything follows. we can have angular displacement, just like we had delta x versus x, position versus displacement. We're going to have omega. That's going to be d theta t dt. And we've already talked about omega a little bit. Remember, this is omega, not w. Try to get used to that. If you call it w, I'll be like, remember, that's omega. I'll try to be nice to you. Okay. And this would be angular velocity. You got all the notes there. Alpha is a new symbol. I don't think we've talked too much about alpha yet. That's d omega dt. Radians per second squared. That's going to be angular what? Displacement, velocity, acceleration. Okay. We've talked a little bit about the terms period. Time for one revolution. Frequency is going to be 1 over the period in hertz. Oops. Let's just say it like this. I'm running out of room. Hertz is Hz, or 1 per second. All right. And then I guess I should clarify here. We've got this. 1 revolution is 2 pi radians equals 360 degrees. Kind of some of our useful things. One of the subtle things, the default, unless you're told otherwise, we usually set theta initial to 0 unless we're specifically told otherwise. Remember how in kinematics we usually assumed x initial was 0? Same kind of deal. All right. We've got our angular kinematics equations. Let's switch boards here. And actually, let's check this out. You guys can probably see this. I'm going to write the x equation really quick. Delta x is equal to v initial x times time plus 1/2 a sub x t squared. And remember that delta x was displacement. V initial x was velocity initial in the x direction. A sub x was acceleration in the x direction. Let's take a look at the equivalent equation for theta. Delta x would become delta theta. What happens to v initial x? What's the angular equivalent of velocity? Omega. So we'd have omega initial. And remember, in these problems, since we're only rotating about one axis, I'm not going to put a subscript x, y, or z, but in theory you could. You could say rotation about the x-axis. But in general, since we're only going to restrict ourselves to one axis, we can do this. What's the angular equivalent of acceleration? What symbol? Does that make sense? And if you look at the units, radians. Radians per second times second. Radians per second squared times second squared. Now you could be saying, well, dude, we can do all this in degrees. We could, but that's a terrible idea, right? And in some problems, as long as you're never going to talk about distances traveled, sure, you could do that. But in general, there's a trick that we can do. And what I want to do is first draw you a circle and explain some of this visually. Okay? Imagine we have some particle here. And it's rotating some angle theta. Okay, so it's moving in circular motion. In that case, let me see if I can draw this pretty well here. If it travels through some angle theta, it's going to travel actual distance. What's a good name for the length of an arc? Arc length. What symbol does that tend to have in mathematics? S. So arc length is S, usually, and different books are probably different, but for us, we're going to use S. Here's the deal. If I want to relate S to theta correctly, I can use the radius of the circle. That's kind of sloppy. Use the radius of the circle. Does anybody know the relationship between S, R, and theta? You can look at the units. S is an arc length. What are the units?
Radians.
No,
Meters.
it's meters. It's a distance traveled. It's an arc length. Theta is in radians. So then let's just write this out. And see if it makes sense from a unit perspective. Meters equals meters times radians. Radians have no units. We're good, right? Everybody cool with that? This is why we want to use radians for this equation up here. I'm going to show you a cool trick. Does anybody remember how omega relates to velocity? Velocity. It's not your omega, it's
Our.
our omega. Remember that? Dom's cringing in the back. So remember, so dumb, right? Let me see if I can draw this. If this is V, and this is the rotation rate, right? Now remember, rotation rate is sort of like the RPMs. Velocity relates to omega the same way S relates to theta. Think about it. Take a derivative on this side, you get meters per second. If the radius is constant, take a derivative and you get omega. Notice we get V equals R omega. Cool. Any guesses how acceleration relates? Gee, there's all the red markers under here. How do you think the acceleration relates to an angular quantity? Here we see distance traveled relates to the angle. Here we see velocity relates to the rotation rate or angular velocity. Acceleration probably relates to the alpha. And now we have to be careful. Is this acentripetal or is this atangential? Atangential. So atangential relates to R alpha. Basically, you just take a derivative to go down here. Cool? Does anybody remember AC? Acentripetal? What was one way to write AC?
VR squared over R.
V squared over R. Now, what was the other way to write it that relates to one of these parameters here? Does anybody remember how centripetal acceleration related to omega?
R delta
R,
omega.
does that have the right units? Check it. Meters times radians per second R omega squared. And remember, that's on your equation sheet if you forget. Notice what's going to be annoying for you. There's different accelerations. One of them is R alpha. The other is R omega squared. That looks a lot like R omega. So make sure you use your equation sheet on test day instead of just, writing it down, or check the units after you write something down. You know what I'm saying? Is that clear? It's easy to screw these up. Well, wait a second. A tangential would be going this way. AC is going this way. What's the total acceleration vector? At least the magnitude of it. How would I get the magnitude of the total acceleration? Yeah. That's a squeaky marker. All right. So notice we actually have about 4 different accelerations here to discuss. And right, there's angular acceleration alpha, there's A tan AC, and there's A total. A lot of times on test 3, I will ask a question and see if you can keep them all straight, because it's kind of tricky, right? We'll discuss that more after we do some practice problems, but it's not uncommon for me to give you a kinematics problem like this, have you figure out omega or alpha or something, and then crank out all the different acceleration terms just to see if you know how to use the formulas correctly. Does that make sense? So we're going to practice with that in a minute. Now I want to show you something here that's a little bit tricky. Notice I did these all as magnitudes. Do you see that? There's no vectors anywhere right now. That's because angular quantities are disturbing a little bit to students at first when you add on the vectors. So because I enjoy torturing students, we're going to do that right now. In this case, let me try and clarify here. Actually, let me just draw a new picture. Okay. If X points this way and Y points up, which way does Z point? I'll remind you of the wheel of pain. I goes to J, goes to K, goes to I, etc. Out of the page. Everybody, even though you don't like me, do this anyways. Line up the fingers of your right hand with X. Okay? Try and curl them to Y. Remember that? X goes to Y. Notice your thumb points out of the page. Do you kind of see it? Every single time for the rest of your life, when you write down a coordinate system, before you do any math, check. Does X go to Y, go to Z, so you don't screw up? Right? Okay. In this case, Z points out of the page. Is everybody okay with that? Did you see that? X goes to Y, goes to Z. Just like I goes to J, goes to K. So now we could talk about this. Imagine we had some beam here, right? And there's a mass on the end, and it's rotating this way. It's rotating about the Z axis. Do you agree? So we would say omega vector is omega in the K hat. And that tends to piss people off. All right? But think about this. We're going to show you a new right-hand rule. Grab that axis and have the fingers of your right hand curl in the correct direction. Watch this. Watch this. Ready? So I know you're working. Just give me your eyes real quick for this one part. I'm going to grab the axis and curl my fingers in the direction of omega. Notice which way my thumb points. Z hat. So what happens here when you write a rotation vector the unit vector associated with the rotation points in the direction of the axis if you grab it with your right hand and curl your fingers in the direction it's rotating. What? If it's rotating this way, it'd be k hat. If it's rotating this way, it would be j hat. What if it's rotating this way? What would it be? Negative I hat. Does that make sense? Dom, anything you want to say about that?
No.
Okay. All right, good.
George says,
Yes.
is that the same right-hand rule for the
This right-hand
square?
rule is used a lot
For
in
the
various
angular?
cases. It's used in magnetism, it's used in torque and angular momentum. So there's two main right-hand rules. X goes to Y goes to Z, or first vector goes to second vector, thumb points in the direction of third. Or the other one is curl right-hand fingers in direction, thumb points in direction of vector. This should be written down for you on page 55. Do you see it? See that vector nature of rotational quantities down there about mid-page? Everybody cool with that? That's the right-hand rule. And then you can see one subtle note at the bottom there. Physicists, yeah, they're the worst. Physicists love to flip their coordinate system if everything's going the wrong way. That way they don't have to deal with minus signs. You know how in a kinematics problem, if everything's moving downwards, we could just say down is the positive direction? In a math class or in a computer code, this way is always positive, right? Counterclockwise from the x-axis is usually positive in your math class. Physicists will just be like, well, dude, if everything's going this way, let's call that way positive. And that drives people nuts sometimes. So just be aware that I will try to alert you if I'm going to do that. All right. Okay. At the bottom of the page, notice we have already kind of talked about that. We've talked about the units. I guess something I should make clear here. All these accelerations, what are the units of all the acceleration terms? These three, AC, A10, A total, what are the units of accelerations? What are the units of angular acceleration? It's angular. What's the standard unit for angle?
Radians. Yes, per radian squared.
Radians per second squared. So remember, A's have units of meters per second squared. Alpha has units of radians per second squared. Does that make sense? We've kind of written this a couple times, but it gets confusing and we forget. A way that I like to remember this, I'm going to show you one last trick before we cruise. Oh, there it is. Okay, check this out. I'm going to rewrite this equation here. Actually, let's do it. Yeah, let's do it. What I would like to do is, for no good reason, multiply every single term here by the letter R. When I do that, what's a good name for R times the change in angle? Arc length, S. What's a good name for R times omega?
Velocity.
Velocity. And sometimes people will write tangential velocity. Just like it's, so it matches up to this tangential acceleration. Sometimes people will put a subscript tan on that. And then what's R alpha? It's not your alpha, it's R alpha, it's
Omega.
no, A10. R alpha is A10. You were thinking R omega is Z or something. I don't know what. So notice, this is what's cool about this. If you know the radius of circular motion and that radius isn't changing, we can actually talk about the distance something travels by first figuring out all the angular quantities, the RPMs, the radians per second squared, things like that. We can figure out all the angles and then just multiply by r and figure out how many meters it travels or how many meters per second. Does that make any sense? There's two underlying assumptions here that we should write. This does not work all the time. This only works in special cases. What's one of the special assumptions that must be true for us to use these kinematics equations? You remember, what was it in chapter 2? That's why I left that up there. So down here, we're going to need constant alpha. Got it? This is going to require constant angular acceleration. We need one axis of rotation. That's something I mentioned earlier. We're not doing multiple axes of rotation. And finally, there's one other assumption here, constant radius. Otherwise, we can't do this trick, right? If the radius is changing, it's going to be much more complicated. Then you would take a dynamics class with Dom. So we're going to restrict ourselves to these simple cases. So far, so good? What do you think would happen if angular acceleration was not constant? How could we handle that? What did we do in chapter 2 when acceleration wasn't constant? Calculus. And another thing that we could do that we saw in lab last Thursday, if you need to do calculus, you could also code. Right? So there's our tools, right? If we could do a problem, if these conditions are met, we use paper and pencil. Otherwise, we're going to code or do calculus or something like that. You ready to do some problems? Any questions about any of these terms? Oh boy. Let's look at 10.1. I'm going to erase the board, both sides here. One of these days, no one's even going to know what a record player is. I hope that's not today.
Don't worry, I have one at home.
All right, sweet. We got the DJ for the last day of class.
You want to listen to Star Wars on from the 1977 record?
Yeah, sure, man. Did I get that right?
Mostly.
Yeah.
It's my favorite record because it's from when the original Star Wars came out that year. It's that first one.
That's pretty cool. I think my dad has that same record. Tom, while I'm erasing, is there anything else you want to mention about this right now, or are you good? Okay, Jules, how about you? Okay. Got it. I'm almost there. Still erasing. Jeez. Need a new whiteboard. Okay. 10.1, here we go. Record player. Okay. Trying to get the magnitude of angular acceleration. Remind me, what symbol are we looking for? Alpha, fish swimming left. If you need help drawing it, I don't know if you saw that. You start here at the top, swoop down, and then come over. Okay, fish swimming left. So that's what we're looking for. Any ideas? What should we do? Any ideas? What did we do in chapter 2 usually? What was our strategy for success in chapter 2?
List all the notes.
List some crap. Let's do that. So now we got to do delta theta, omega initial, omega final, alpha, and t. So instead of x, v, final v, it's right now it's these listed knowns and unknowns. Do I know delta theta? No. Do I know omega initial? It's rate. Oh, it's a rotation rate. Is anything in here a rotation rate?
RPM.
RPMs. I want you to associate RPMs with omega. Now we need to remember omega is supposed to be units of radians per second, but we could do that. That's just a conversion. So let's just say 33 revolutions per minute. That's what an RPM is. Revolutions per minute. Okay. Immediately, I feel uncomfortable. Let's get it into radians so I don't screw up. What's the conversion? Does anybody recall? How many revolutions for radians?
2 pi.
2 pi radians equals 1 revolution. Okay. When you're punching stuff in your calculator, this is one of the more common mistakes. Sometimes when we're going from radians to rev, you'll see, whatever. Minutes, that's a bad unit for a physicist usually. What can we do with that?
60 seconds per minute.
Make sure you put the units in the right spot so they cancel out. Boom, boom, boom. We got radians per second. Notice, do a quick check. Trust me, always do this. 2 pi, isn't that about 6-ish? 60. What's 6 over 60 about? 0.1. So it should be about 3. Do you agree? Always do that check in your head because this is the conversion people screw up for some reason. Whatever. So let's punch it in. Anybody got the units already? Is it 3.0459 or something? What is it? I forget. 33.333 times 2 times pi div 60. Oh, 3.4906. My bad. Now, we obviously don't need that many units, so let's just keep it to 3. I'm going to underline it right there so I remember later on we can round it. What's omega final?
0.
0. How do you know? Comes to rest. And then here, I hope you agree, this is 10 point. I'll just stick an extra sig fig there. 10.00 seconds. Let's assume it's good to 4. All right. All right. What was next when we did chapter 2? We listed our crap. Then what? Equations. Okay. We've got what would be another equation? Does somebody want to give it a shot? What was the V equation? Does anybody remember?
B final equals B squared plus AT.
V final equals V initial plus AT. So what would be the equivalent in rotation land? All the V's go to omegas. All the A's go to alpha, fish swimming left. Okay, notice it's important to draw your alpha distinct from the letter A, right? Some students will draw their alpha and it starts to look a lot like a letter A. It's really hard to read. Wait a minute, is that going to do the job?
Yeah.
We know it all. Okay, so that's it. We could, what's the last one anyways? Just so we have them all. Omega final squared should equal,
B final squared.
which becomes omega initial squared plus 2ax becomes 2 alpha. What's the equivalent of x?
Theta.
Got it? So we're going to snag this one, right? That gets the job done. Okay, let's crank it out. Let's solve for this algebraically because it's pretty easy at this point. Then plug in. We can check the units. Looks great. Radians per second divided by seconds. That's radians per second squared. The units check. Looking good. What do we get? Omega final is 0 minus 3.4906. Oh, shoot. I forgot to write the units on this one. What were the units on this 3 point blah, blah, blah. Sorry about that. What do you get for alpha? You shift to the decimal place, right?
-0.349.
So far, so good. Just in case we need this number for a subsequent calculation, I'm going to round like that. I'm going to indicate that I'm going to round in the 9 just to irritate Dom a little bit. If you were on a test day, right, you should just round it to 3, but whatever. So did we solve the problem? Are you good with that? Everybody happy that we got the job done? No, why not?
It's squared.
Oh, good, good. That wasn't even the mistake I was looking for. What's the other one? Magnitude. Ah, don't you love physics instructors? Every once in a while they ask you for the magnitude of something. Magnitude shouldn't be negative. Do you agree? Oh, those dirty physicists. Shame on them. So far, so good. Just watch out for the word. Remember all this stuff in chapter 2, how you had to pay attention to speed versus velocity versus et cetera, et cetera, et cetera. Distance versus displacement. All those things come back again. Dom, anything you got to say?
Yes,
What?
that's a big, magnitude is a very important word to consider because you want to know, because we could do it different ways, right? You could say clockwise is positive, or someone else might say counterclockwise is positive. So one person will get a positive answer, one person will get a negative answer. We want to see that you understand when you do a calculation, which way things are going. So not only might we ask magnitude, but which direction. So that allows you to go from math back to the physics of the problem. Pay attention to magnitude. Magnitude better be positive. No matter if you get left, right, up, down, clockwise, counterclockwise, wrong. Positive, positive, positive.
Which, building on what Dom said, sometimes, to be fair, on test questions, a lot of teachers will ask for the magnitude specifically because then we don't have to worry about which way you drew your coordinates, right? So it's a convenient way. We should all get the same answer for magnitude, regardless of how we draw our coordinate systems, right? But we're going to get different answers for direction based on how you, right? Somebody might say plus or minus, like Don was saying. Yeah, absolutely. Yeah.
So what you meant vector is that acceleration?
Ah, in this case, we didn't specify, did we? We didn't draw a picture, did we? So I kind of was a bad person. I jumped right into the equations here. So we should probably draw a picture of this. And maybe I could draw a picture of a record here. And an axis like this. And maybe this is X, this is Y, and this is Z. So then the record would be rotating about this, which would be what direction? If the record, whoops. Isn't this normally how a record player looks? There's a record on a flat surface. Usually we would call that X and Y. And so it's rotating. This is the direction it's rotating. Right? And so which direction is it angularly accelerating? The other direction, right? So according to this, it would be negative, what unit vector? Yeah, negative k hat. Is that good? Yep. Now, again, because we were looking for the magnitude, we didn't need that. That's why I didn't really talk about it. So that's an advantage of asking for magnitude on these questions, is then everybody can draw their coordinates however they want. Cool? Good. All right. Ooh, part B. I'm going to switch boards. Part B says, mag of total accel. And I'm going to show you a cool trick here. I want the magnitude. I'm going to emphasize that just so I don't screw up any minus signs or something later. Does anybody remember the equation for how we get A total, the magnitude?
The square root of AC squared plus A tangent squared.
Absolutely. Does anybody else, nice job, Michael. Does anybody happen to remember the equation for AC in terms of rotational variables, R, omega, stuff like that? Alpha. What was AC? It's not your omega squared, it's, oh my gosh, geniuses. So it's R omega squared, and then I'm going to square it. Does anybody remember A tan? Not your alpha. Excellent. Well, wait a minute. Don't we know omega and alpha here? Ooh, we got to be careful. We need to get this value at 2.00 seconds. Wasn't it at 2 seconds? Oh. Sorry, I forgot to write the whole question down.
Well, 2 seconds before something.
Oh, 2 seconds. Ah, before coming to rest. So at what time?
8 seconds.
Nice job. So we want it at 8 seconds. You agree? And we need alpha at 8 seconds. But wait a minute, is alpha a constant or not? In this problem, did we make the assumption that alpha was constant? Yeah, so there we don't have to worry. So how can I get omega at 8 seconds? Any ideas? For those on Zoom, I'm going to flip back to this board.
You just plug in the first equation at the top.
Yeah, we could use this equation again because we know omega initial. We basically have to do a new problem where we know the time and we know we could look for omega final. Agreed? Okay. Let's do that real quick. Now we know alpha, so it should just be plug it in. What was omega initial? Was it 3.491. Plus alpha, here's where I'm going to use that, right? So now this is kind of important. I just want to mention this. Okay. We want to use the alpha variable. This is why I didn't round all the way, because now I want to use the unrounded result over here so that I don't introduce intermediate rounding error. You know what I'm saying? So, right, if you use this rounded number, there's people still doing that and they're getting numbers off in the third sig fig. So let's use the unrounded result over here. Negative, what was it? And then we could stick in our 8.00 seconds. And we're off to the races. I'm pretty confident you can plug all that in. Now notice, there's one last piece of information we need to do this. I'm confident you can plug in some numbers. Did anybody get the number for it?
0.9678.
0.9678. What are the units?
Oh, sorry, 697.
Oh, 6978. Sorry, my bad. 6978. What are the units?
Meters per second.
No,
Oh, right.
radians per second, right? Remember? It's just getting used to that new, right? So there's a little to get used to with units. We're going to round that in the third digit, probably. I don't know. I could check, but let's not. In this case, alpha is known. We know alpha from the previous problem. Alpha was, well, this is alpha right here. How do I get R?
It's given, but it's the same.
Okay, okay. How do you know we should use that radius? Or should we use some other? What's the thing in the problem that indicates we should use the radius of the record?
It's constant.
There's a word written on the screen near my head.
Oh, the left.
This is the thing that tells us where. So because it's telling you this, it always matters which point you choose. I have a simulation, maybe I'll show you after the break, that will tie this all together. But yeah, so far so good. I think at this point, you know all the pieces, you could plug them in and get the number. So I would like to actually go to part C in the interest of time. Or do you guys want to see it? You want to see it worked out or not? Is everybody okay right now? Thumbs up, thumbs down? Okay, so we should move on then. Okay, you've got the solution if you want to check it at home. I want to focus on part C. Oh, and then do you agree we don't have to worry about the plus minus sign here? We're getting a magnitude, so we're just going to use the plus sign. Okay, part C. Distance traveled by point on rim as record comes to rest. Or was it 8 seconds? Which was it? As it comes to rest. Okay. What is that? I want the distance traveled by a point on the rim as the record comes to rest. What thing am I looking for? The magnitude of what?
How about the name for the data?
Of the theta thing?
Yeah, that was a.
Angular displacement,
Yeah.
you mean? That's not it. Let me ask you this. This has what units? Distance has units of meters, right? Does delta theta have units of meters? Arc length. Does that, which relates to delta theta? Delta theta would give me the angle, and then I just multiply by. Exactly. So distance traveled by a point on the rim, let's remind ourselves, point on the rim, that's just telling us R equals the full 24 centimeters. Okay, so what we could do is get delta theta equals omega initial t plus 1/2 alpha t squared. We know this, we know this, we know this, we know this. We can get delta theta. And then how do I get the distance traveled? That's the arc length. And you got it. Feeling good on that? What units do we have to use to get this part right? If I want this to be in meters, the radius is going to have to be in meters. What about theta?
Just for
Radians. That's why we want to use radians per second and radians per second squared, and that's why I immediately get rid of RPMs. To be fair, there are some problems where you don't need to convert. But in general, as a beginning student, one of the most common mistakes is you don't get everything in radians, and then you start doing acceleration terms and different things, right? This had to be in radians per second as well, otherwise it's not going to work. So if you're not sure, go to radians per second, do the whole math, and at the end of the problem, you can unconvert if you have to. And as you get more experience, you'll learn the situations when you don't need to do all the conversions. I don't know, Dom, any thoughts on that?
Yeah, stay in radians.
It's just better. You don't know when you're going to have one of those questions pops up that you need it, right?
All the calculations are.
Yeah. Calculus is in radians. This is in radians.
Your circumference of the circle is 2 pi radians times r. It's not 360 times r.
Yep.
Key stay in radians. We think in degrees because it's easier, but we know what a degree is. We know 90 degrees, but yeah, convert at the start and at the end.
Yeah.
Into and back out in radians if necessary.
Remember when we did that code of arc? Remember how I had you code it? We thought in degrees, so we wrote down the constants in degrees, and then the very next step in the code was convert to radians, so the code could do everything correctly, right? So a lot of times what you do at the end of a problem, like Dom was saying, is you can unconvert to radians if you want to help other people understand, because other human beings can relate better to angles in degrees, but do all your work in radians and then unconvert for them at the end. Yeah, all right. Should we try one more before the break, right? I'm going to look at 10.2. Oh yeah, we're going to Kaohsiung, people. Kaohsiung is a town in southern Taiwan. So I lived there for a while when I was on sabbatical a few years back. Pretty cool. But now I get to talk about these weird train stations. So while I was there, I was trying to write this workbook. And I'm like, oh, I could use these train stations for these weird rotational kinematics problems. And I thought it'd be so cool. But in the end, they're still just physics problems. Still erasing on Zoom. In your classes, Dom, do you do a lot of kinematics with rotation or not really?
Yeah.
Okay.
Whole chapter.
Okay. You feel like this is an adequate introduction for them in that sense that they're seeing a lot of the same things they're going to see later?
Yep.
All right.
Pay attention.
The same kind of mistakes they make over there at the units mainly?
Yeah. You radians or degrees, and you give a magnitude.
Gotcha. And do you do a lot with A10? And well, you guys call it something else over there, right?
Depends.
But sometimes A10, sometimes a parallel, a perp, maybe, or a normal, or something, right? There might be different terms.
Tangent and normal, radial and theta.
I got you.
Norming theta, tangents and normals.
Got it. So there might be some different terms, but at least you'll be ready for the math and some of the basic mistakes people make. Uh-oh, hopefully. Shoot. Oh, well, I was only halfway on the screen for that last problem. Sorry, Zoom. I don't know. You got the solutions in there, so it's not a terrible thing for one problem to be a little off. Sorry about that. I do apologize. I'll probably do it again tonight, so you can watch it there. All right, 10-2. Now we're going to take it up a little bit. Here's Central Station. Here's San Duo. You can Google this. Actual stations. It's supposed to be a quarter circle. Obviously, in the real world, it's not a perfect quarter circle, but it's pretty close. So it has some radius. It leaves Central. Speeds up at rate. I guess we'll magically ignore the fact that it has to stop when it hits the next station. It's going to go at constant speed, whatever. Maybe it's an express. Okay. All right. We want the angle through which the train accelerates. What's the first step in this type of problem? What was the first thing we did in the last problem? Yeah, so let's identify what the heck these symbols are. What is 1.40 meters per second squared? What is that? What acceleration? We've got 4. Tangential, because that's the speed. Remember, A tan was the change in the rate of speed. You guys good with that? This is A tan. Nice job. That's the tangential acceleration. That's the rate at which it's speeding up tangent to the circle. It's not going towards the center at that rate. Okay. It hits this speed. What is that? Is that an omega? No. So it's just a, yeah, that's probably the final, right? R, that's pretty obvious. So now we could write down some information here. I've got V initial equals 0. V final equals 25.7 meters per second. I've got A tan equals 1.40 meters per second squared. If you're curious, I looked it up. They said that basically if your acceleration exceeds this, people start to get nauseous. Something like that. I believe that was an actual train number. 25.7 meters per second is about how many miles per hour, if you had to guess? About double. So about 60, maybe 50 to 60 miles. So these are realistic train numbers, okay? Okay, what are some other things? Do I know the time in this problem? No. Okay, what makes sense? What's the other variable I might write here? We're talking about meters per second. Meters per second squared. Should I be writing a delta theta up here? Is this change? I would not write change in x. That's a bad idea because that doesn't represent this problem well. It's not changing radius.
Oh, arc length?
Arc length. So S is the other variable that we don't know, which relates to, you see where this is, you see this pattern here? Basically, I try to trick you by giving you some units of meters per second and asking you something in radians. Or giving you a bunch of stuff in radians and then asking you for stuff in meters, so you have to convert between rotational and, you see the pattern? You constantly have to convert back and forth between rotational and translational quantities in this problem. We do know that S is equal to R theta. We know R, we're going to be able to get the variable we want. What's the next step? We've written our knowns. What's next? What equation might I write? Can you think of an equation that involves this crap? Particularly one that might involve arc length. If it helps, give me your kinematics equations in X that you have memorized. Delta X equals. So what would be the equivalence here? Instead of, like you were saying, I'd write a delta X instead of, so it's just this one subtle thing. Instead of delta X, what could I write?
S B tan times C equals 1/2.
Yes.
T squared.
Right? And so I'm not going to fill up the equation sheet with all of these. You might take a second to look back there. You have to know how to take the standard X equations. The X kinematics equations are right here, and you have to know how to rewrite those in terms of the tangential or the thetas, basically. Does that make sense? So, right, after you do a few of these, it'll be easier. It's just been a while, right? Well, in this case, I could divide by R, and we got the answer. You can plug in numbers, you're good to go, right? Oh, wait a minute. We don't know time. Is that going to help? That's not going to work. Let's try another kinematics equation. Give me another one instead of the delta X. In particular, we need one that doesn't have time in it. Can you think of one? What would be the equivalent? Oh, what's not that? What's the end of that equation? What would be the equivalent here? V final X, wait, V final would be V tan final squared equals V tan initial squared plus 2A tan. What would delta X become? S, which is R delta theta. So I'm going to cheat a little bit just to make room. At this point, we could plug this in and we got it. You see that? We can solve for delta theta at this point. Is everybody cool with that? I'll give you a second to see people go right. How are you feeling on this? Thumbs up, thumbs down, thumbs sideways? What do you think? Sideways, what are you thinking? Okay.
It's kind of like the idea that S could be like X, because like X is like curved.
Yes, it's just the meters along the curve. That's what S means, right? As opposed to meters along the x-axis. Same thing. V10 is meters per second along the curve. A10 is meters per second squared along the curve. So instead of having an x-axis, we have a curvy axis, basically. Is that helping? Yeah. All right, what's the next part? I think you could solve that. Okay, get some times. Ooh, I'm gonna let you try part C, D, and E at home. But there's gonna be some surprising stuff when you see these things. Well, let's try part C really quick. You know what? I'm gonna let you do it at home because it's time for a break. But I would definitely finish out this problem at home, okay? Because at this point, you know how to set it up. If you follow it through, the plots might surprise you. So you don't have to try and be perfect, but try and sketch what you think they would look like and then actually look at the plots. All right. Yeah, let's go ahead and take a break there. Let's take a break. Okay, so I got 12:13 here.
Your heart.
What's that?
Out of the goodness of your heart.
That's what I call it. I have a strange, right? To be fair, right? I know I'm a tough instructor, but I absolutely care about your success in the real world. And I make my assignments and everything I do, I think about, is this going, now, I might be wrong many, many times, but my hope is that I'm doing things to help you, not hurt you, right? That doesn't mean I'm always doing them well, or maybe my beliefs are misplaced or whatever, but I am trying to help you. All right, so with that said, let's take a look at this right here, right? Trying to understand this stuff without seeing stuff move is torture. So I'm going to walk you through this code really quick. So here are some constants, right? The initial angle is going to be 30. My rotation rate in radians per second right there. Can you guys see that all right? Or does it need to be bigger? It's big enough? What's that? I can't hear you.
The gray is a little white.
The gray is a little light.
Yes.
Okay, sometimes you may have to look at a different screen too, right? I guess I kind of got to do it. I think I got to do it at about this size here. Whoops. So I could see all the text. So I apologize if you can't see it all. But basically, these are some constants, right? This is like our table of constants that we've been drawing. Okay, sim speed, whatever. That's just something we'll talk about. Here's just it's going to run for 4 seconds. That's great. Maybe let's slow this down to 2 seconds. How about 3.25 or something? All right. dt is just our time increment. A pivot is just going to be a sphere in the middle of the screen. Rod, there's going to be a cylinder, and this bug, there's going to be a sphere that I draw on there, and that allows us to choose points other than the end of the rod. Okay, so just whatever. Now notice we can change these into vectors. It's a little bit complicated, but what I did is I created a vector called the rotation axis. So in this problem, I think the rotation axis was just z. Let me go back up and look. The rotation axis is 1. That's basically k hat. Do you agree? 1 in the z is a k hat. So in this case, omega is in the z direction, alpha is in the z direction. This is going to be a radius, right? It's going, remember that r is what? Final minus initial. So it's going from the center of screen, which is where the pivot is located, to the bug. And notice, this is something we've been kind of glossing over. You're going to need cross products. It turns out to convert these magnitudes into vectors for the velocity and a tan, we actually need a cross product. I've been kind of glossing over that. I'm still going to gloss over that. You probably recognize that. A centripetal is r omega squared, right? And so when we're doing these rotation codes, man, you have to be really careful about vectors versus scalars. In particular, this one looks like it's going to be a vector, but AC, it right here is a scalar. Ugh. Anyways, more on that down here as we go. Okay, some boring stuff. Here's the code. What I'm going to do every time is I'm going to use my derivative calculations that we used in class. So basically, omega is, or alpha equals d omega dt. Rearrange that, you get this equation, etc. updated. You can use that to get the change in the angle. Omega is d theta dt. You can rearrange that. And so notice we have to be careful with the plus minuses. If you want to learn more, we could talk about this after class. But then I'm going to rotate the rod, rotate the bug, and then I'm going to recalculate these vectors, recalculate the radius vector, and then we see the same calculations over and over. When I run this, let's watch it. So the blue ball there that you can see right now is the bug. We can change the color of that if you want. And we see all these different arrows. And notice below here, we can see the angular displacement versus time, right? And we could try different parameters here. We could try making alpha a lot bigger. How about like -3? When we run this thing, notice we see all these crazy arrows. Whoa, that's pretty cool. So here I blocked the auto zoom, I think. So maybe let's go to a smaller level. let's say negative 0.5, and let's run this. What are those three arrows representing? Can you tell? I know there might be some colorblind people, but what is the red arrow that's disappearing right now? What's that? Centripetal acceleration. What is the blue arrow and the purple arrow? Let's run it again and watch them. What do those look like?
Blue one looks like the velocity one, the purple or pink one looks like the atangential.
Correct. Excellent. And so, and if we wanted to, we could try and represent the alpha and omega vectors. Which way would the alpha and omega vectors point? Remember what we said about angular quantities? We don't want to say counterclockwise. So what unit vector represents omega? Out of the page, k hat. Remember that? Grab that axis. So, right, in this case, it's rotating this way. I know you can't see this on Zoom very well. But right, if it's rotating out of the page, right, omega would be k hat, right? And so maybe I'll just draw it like this. That's the omega direction, right? So we would say that the omega vector is equal to omega in the k hat. All right, so I just wanted to point out that if you wanted to visualize something and help someone else understand, coding could be a good way to go with this. As you go on in engineering, more and more things are in coding or MATLAB. So it's important that you practice these skills, even though they're difficult. Any other questions about this? For now, that's good. Did that help, or was this worth seeing it or not? Thumbs up, thumbs down. What do you think? Okay, sometimes just seeing something move helps, right? Okay, all right. And if you want to play around with that, talk to me later and we can look at it. Let's go back to getting this out of here. Take a look at 10.3 in the book. Well, I'm getting organized up here. 10.3. Santa Ana's a M205. Thanks. Just get the screens up, Zoomer. $10.3. Oh, this is a flashback to chapter 2 as well. We have a flywheel, basically a disc. It's going to rotate about this axis here, right in the center. The radius is 0.20 meters. Looks like we're not caring about sig figs. That's fine with me. We've got this mass that's attached here with some super glue or something. And it's 15 grams. Again, not caring about sig figs. Okay. And we've got a plot of omega versus t. This is time, this is omega, and time is in seconds, and this is radians per second, I hope. Let me see if I can draw this plot pretty well. This is 2, 4, 6, 8, 5, 10, -5, -10. looks like it doesn't even go down to -10, does it? And it stays on for 1 unit. Then it goes up to 5. Then it goes over. Like that. So that's my attempt to draw the plot that you have there. It's not perfect, but it's close. Whoa. And then we're asked this question. This is hard. Okay, it's a logical question. At what time is the mass going to return to its initial position? Anybody have any clues? And I think at what time does the mass, yeah, okay. So let's say it like that.
Is it like on the area of 0?
Area, exactly. Nice job. Remember when so we're doing chapter 2 graphing tricks, and area under omega t is what? So the area under a VT was delta x, not x, delta x. So the area under omega t is
Delta theta.
delta theta. And so if delta theta is 0, we're back. Can anybody just see it?
Wait, what?
At 4 seconds, right? Because we're going to have a positive area. Let's call that area 1 equals, what's that going to be? Can somebody help me?
What?
Yeah, you're right, because 1/2, 2 times 5 is 5. What units? So we can see that has the right units for delta theta. And then over here, what's this area? Area 2 equals -5 radians. Does everybody see it? So the answer, well, I guess that wasn't hard for you guys. Nice job. The answer is t equals 4.0 seconds. Nice job. What do you think? So far, so good? Everything in chapter 2 comes up again. Yay. All right. How far has the mass traveled after 8 seconds? What do you think I'm asking here? What's that? Arc length. I agree. The default assumption when you say how far is meters. But do you agree this question is probably vague? Because it's not clear whether I mean arc length or angular displacement. So the default would be how far. Usually we think meters. That makes me think S, arc length. Whoops, that looks like a 5. How do we get arc length? What's the general formula relating to angular quantities to get arc length?
Or the delta theta.
R delta theta. How do we get delta theta? From area under curve. Oh, crap. Why did I say, oh, crap?
Because you have
Oh, time.
because like it says distance traveled.
It's distance. This is a distance. Do you remember the issue with distance versus displacement? For areas? Do you remember?
It has to be the magnitude.
What's that?
It has to be the magnitude.
Yes. Oh, crap. So if I call this area 3, and if I call this 4 and this 5, we'd have to get the, so how about I say it like this? Distance would equal the absolute value of each of these areas times the radius, right? So it'd be radius times absolute value of area 1 plus, you know where I'm going with this now? Absolute value of area 2 plus absolute value of area 3, etc. Oh my gosh, that's a lot. Oops, I forgot a bracket. Did I lose anybody on that, or did that make some sense? Right, when we're getting distance, right, displacement would be r delta theta, right? And that would tell you the final location, or, well, how far it traveled relative to its initial location. No, it wouldn't. It would tell you where it's located relative to its initial location. But if we want the distance traveled, we got to get the absolute value of those areas. So that's a subtlety. I hope I'm making that clear. Probably not, but hey, I'm getting paid either way, so that's cool. All right, not my intention to be unclear. It's just I'm naturally good at it. Okay, C. How do you get the plot of alpha versus T? How do you get that plot? Slopes. Yeah, nice. You guys are doing pretty good. So you're basically making a plot of the slopes. What do you think, Dom? Are they doing all right? I thought this was going to kick your ass, but you guys are doing solid. So you guys should be proud of yourselves right now. You are clearly learning something. Okay, that's awesome. So obviously you're going to want to do that at some point. How will we get A tan versus T? So let me go over here. Actually, let's make that plot really quick. I'm going to set up here. Give me just a second. I'm going to zoom out a little bit. Whoops. Okay. This is not going to be the most perfect plot here. I'm going to try to do it while I have everything on screen. So let's take a look. What's the slope from 0 to 4 seconds? 1, 2, 3, 4, 5, 6, 7, 8. So from 0 to 4 seconds, what's the slope?
-5 maps.
Okay, so negative 2.5. So let's just say here's 5, here's 5. So this is 5, this is negative 5. So it should be right there, right? Okay, and then the slope here is 0. How about right here? What's that one going to be? 10? No, 5. Wait, what is it? In 1 second, it goes up 10.
Yeah.
Crap. All right, 5, 10. Here we go. Sorry, this is kind of sloppy. All right, so there, the positive slope, and that's just for 1 second. Okay. And then the last one, it looks like it goes down to what? Positive 2.5 again. Goes up 5 in 2 seconds. Something like that. So it would look something like that, right? So that's alpha as a function of time. What are the units on alpha? Remind me the default. Radians per second squared. And that's right, that makes sense because we're going to have radians per second over seconds. Rise over run, the units of rise over the units of run. Okay. Sorry, that's so sloppy. let me just reorganize this so it looks a little bit better. This was part C. Okay. And part D. How do you get A tan versus T? What's the equation for A tan?
R.
R alpha. So how would you get it?
Multiply,
Just multiply everything up there by the radius. Yeah.
Yeah.
And then it's a question of, do you want the magnitude or do you want to include the minus sign? So there's a little subtlety. Are we talking about, so maybe I'll put think. Do we want A tan mag or plus minus sign indicating A tan direction? And that's going to depend a little bit on the situation and what's going on, but essentially you're going to multiply by R, then think about minus signs. You may want to include it, you may not, depending on the context of the situation and who you're talking to and what needs to be done. Good? All right. How would you get AC versus tan? Or sorry, AC versus time. I said tan. I apologize. How would you do that? What's an equation? Give me an equation for AC.
R omega squared.
That's right. Do we have a plot of omega versus time?
Yes.
So what will we have to do to that plot? Square every number on that plot. And wouldn't it be a lot easier to do this in Excel and just make a column of data and just square it and multiply by R? So we could square every omega and multiply by R plot. Now, I have done this for you. If you wanted to see if you could do it, you could just take this calculation home, generate the plot, square it, and make sure you can do this. I am a firm believer that graphical literacy is important to your career. Again, I'm not trying to waste your time with the coding. I'm not trying to waste your time with graphs. Graphs come up in the real world. They contain a lot of information in a small space. And being able to create them and read them and interpret them, understand them, is a useful job skill, in my opinion. That's just me. Dom, what do you think? Do you do stuff with graphs in your class or not?
Yep.
Yeah, so got to be able to graph. Okay. Ooh. Yeah. I know I'm just kind of giving you big picture here, but a fun side question here. At what times is acceleration of the mass 0? Now, when you see this, there's one thing that I really want you to get out of this question, okay? And here it is. What do I mean by acceleration? In this question, what do you think the default meaning is of acceleration? Total. And so this is what's annoying. We've got all these accelerations and you're like struggling to keep up with all these definitions and units. And then somebody throws this question here. They don't specify what they mean. That implies total acceleration. And that is a tough thing for students to deal with. As written, that question says acceleration. I'm not talking alpha, I'm not talking A10, I'm not talking AC. I mean A total equals the square root of AC squared plus A tan squared. Okay? So that's what you're supposed to figure out. Do you see any times where A total will be 0? In particular, do we see any candidates on this plot? At what time does this component of acceleration equal 0? When will A tan equal 0? Between 4 and 5 seconds, alpha is 0, so A tan would be 0. If we go back to the other board, whoops. Between 4 and 5 seconds is AC equal to 0?
So it's never.
Never, right? AC, omega is non-zero, so omega is, right? If omega is non-zero, AC is non-zero. At this point, there's always some acceleration for this mass, right? Even when it's at rest. Do you see that? At the instance it's at rest, at 2 seconds, and what is this? Probably what, 5.5 seconds, right? At those 2 times, it's instantaneously at rest, but it's still accelerating because A tan is non-zero at those times. It's speeding up in the tangent. Oh my gosh, what a mess. This gives you an inkling of how complicated rotational problems can be. How would you get the largest force? G, largest force? Crap. What would be the procedure to get the largest force? How does force relate to anything we've been talking about? F equals ma, right? Which A? Exactly. So you'd have to go through and look for the largest A total, and that would take a lot of time. But I just wanted to emphasize this one silly little thing here, is that you can look at these plots can tell you something about the force. Isn't this amazing how much information is contained in this one plot? Think about this. I don't know, I'm tingly all over. I don't know about you. Look at this thing. We had some screwball plot. We get the rotation rate, and that's it. We could record the RPMs. You could have a tachometer that's recording this or something. You could do a video, whatever. From this, we could actually figure out the forces on this thing as a function of, it's incredible how much information you can get out of a plot. That's what's so cool. I don't know. I find that neat. I hope you do too. Lastly, how do you get RPMs from here? How would we get RPMs? What's that? Yeah, what's the conversion? To get RPMs, we'd have omega times what? These are units of radians per second.
60 seconds over a minute. 2 pi.
Which, where is it?
1 revolution over 2 pi.
Yep, 1 rev over 2 pi. Now, I know you're tired. I know this is boring. Please, please, please put parentheses around this when you punch it in on your calculator. You know what I'm saying? I know Dom does. He's nodding because we've both seen students screw this up. What's the conversion factor approximately? About 10. So always think that to make sure you do. So do you agree it should be going from about 50 to about negative 50? If you keep that in mind, just say, what should it be? That will help you check your parens. How do I know? I've screwed it up a lot. When I was in school, I screwed it up. All right. Got to remember those parens. All right. So far, so good. Now, Is this helping you or not? I'm not doing every single step of every problem. What I'm trying to do is say, these keywords mean do this. Is that enough to help you succeed or not, or is it too early to tell? I didn't do every step of every problem. Is that okay or not? Too early to tell. Okay, all right. Well, I'm gonna do more of it, right? And I know that you got the solutions. Let's take a look at the next problem, 10.4. See if you can see what, I'm gonna erase the board, 10.4. You guys are doing great today. I'm impressed. Okay. Ten point four. Got a flywheel here. Always the flywheel. This picture's not the greatest. Okay. We're told that this is X, this is Y, and this is Z. What should you check every single time you draw a coordinate system? Right-hand rule. X goes to Y, goes to Z. Looks good. X goes to Y, goes to Z. Looking good. Okay. Part A. Units. What are the units implied on each of these constants? We should always know what units are implied.
Radians per second squared on 8.
How are you getting that? Kind of tell me what's the process.
Because you need radians per second for omega. And since you're multiplying by t, that means you have to
Yep.
you have to reduce one on the bottom.
If I write that, do you agree that's the same thing as what you're saying?
Yeah.
The units of 8 times the units of time have to equal the units of omega. So the units of 8 equal the units of omega over the units of time, which the default will be radians per second squared then, radians per second per second. And then, do you agree the units of 6 similarly? Is that going to have an extra second in the basement? So that's going to be radians per second cubed. Always check your units. Good. B. What unit vector is implied on this omega as a function of time, according to this picture? It rotates in the XZ plane. Exactly. You know it's not X or Z. Right? If it's rotating this way or that way, the unit vector has to be j hat. Now, because nothing else was specified, the default assumption would be positive j hat. There's a lot of assumptions in these, isn't there? It would be, now, I would try to make that more clear on a test question, but this is supposed to be for lecture. I'm trying to help us think. So if you were on a test question and this was unclear, you could say, which axis is this rotating? They'll tell you. All right. But in this case, right, unless I specifically asked what is implied here, right, you can ask me and I'll tell you. All right. Not trying to trip you up, just making us think. Oh boy. Number of revs. Woo! This one's juicy. The number of revolutions completed when it has maximum rotation rate, oh, in positive direction. All right, that's a lot to unpack. What is number of revolutions? What does that phrase mean?
RPMs.
What's that?
RPMs.
No. RPMs would be revolutions per minute. This is just revolutions. Do you agree?
Oh, the frequency.
Not frequency. What does revolutions convert to? Radians. So radians is what symbol? Delta theta. Nice. So we're looking for delta theta. Do you agree? What is this? Max rotation rate. What symbol does that mean?
Is it when the function is 7 months long?
What symbol, what function?
Oh, the function of the neighbor.
Yep. In the positive direction here. Okay. How do I figure that out? Which kinematics equation should I write? Should I use the delta theta equation? Should I use the omega equation or the omega squared equation? Nope. We can't use any of those because it's not constant acceleration. Do you see it? There it is. This is not constant. If you take the derivative of this, do you get a constant? So is acceleration constant? No. So we can't use any of the. So here's the example. Take the derivative. Did that make sense? Remember when we did this in chapter 2? Take a look. What is d dt of omega of t? In this case, that should be alpha of t. Agreed? That's what it means. We take the derivative. Look, radians per second is radians per second squared. What do I get when I take the derivative? Somebody help me.
8 minus 12t.
8 minus 12t? Okay. Do you agree we can figure out the units if we needed them? We're not gonna right now. Do you agree that alpha is not a constant? So that's why we can't use any of those kinematics equations for constant excel. We have to just take the derivative. When is omega going to hit the maximum? How do I figure that out? Set this to 0. What's t? 8 over 12 is what? 3/4?
Or sorry, 2/3.
2/3? So how about 0.66667? We'll underline it there, seconds, right? Probably don't need 5, but whatever. Let's get it to 66. That's good enough. Agreed? So now what? How can I verify that's a maximum?
Pick a value.
Okay, true. I was just gonna say, take a second derivative. If you take another derivative, yeah. Note. D squared dt squared of omega is equal to d dt of alpha is equal to -12. Right? Concave down, maximum. You know what I'm saying?
Also, the negative value implies that it's maximum.
Yeah. What's another way to tell this? Plot the damn thing and look at it, right? And that's what we should do, right? I can't write. Is this a good review of chapter 2? I hope you understand now why chapter 2 was so punishing. You guys are really doing a good job on this, right? You suffered in chapter 2, and now this is a piece of cake, hopefully. Or maybe I don't know. It's better than a punch in the face. Finally, how do I do this now? So now can I plug into this equation? We've got the time. I've got alpha. Can I just plug into that? No, this makes no sense at all because it's not constant. So I can't do that. How do I get an equation for theta?
You take the integral.
Take the integral. So then here, if I integrate delta, or well, don't forget, theta does not equal the integral of omega dt. Delta theta equals it. You know what I'm saying? The change. All right. Just venting a little frustration from 15 years of saying the same thing. Okay. All right. And then at that point, cool, we're good to go. Does it say anything about the initial value of theta in this problem? Take a look. In 10.4, does anybody see anything specifying the initial value of theta? I don't.
No.
So in this particular problem, we often assume theta initial equals 0. And then if that's the case, then the integral would be theta. Is everybody okay with that? Only if we can assume that. And in this problem, it doesn't say anything. So we're good. In the computer code that I wrote, that I showed you earlier, did you notice theta initial was 30 degrees and we couldn't have done that? Something starts at a non-zero angle. Okay. Part D. I'm going to squeeze that in right here. When does wheel reverse direction? How would you figure that out?
Omega t. Set equal to 0.
Set omega of t to 0, right? Velocity is 0 at max height. That's when you reverse direction. So far, so good. Does that make sense? Whenever velocity is 0, you're transitioning. Usually, I guess it could be an inflection point, but yeah, we're gonna, all right. And then part E. No net force. When you see the word force, oh, and it points on the rim. What am I asking there? When I talk about force, I'm basically asking you about a total. Well, we have equations for omega and we have equations for alpha. Do we have an equation for A total? You bet. We just shove in the equations now. And then solve for T. And then the last one is make some plots. I think you could do that at home with Excel. Got it? We're almost there. We're almost there. The questions that I'm asking on this page, you can see, here's 4 questions we've done today, 10.1 through 10.4. There's a lot of different ways I can mix this up. Acceleration could be constant and we use kinematics and word problems, or we have problems where you have functions and you just take derivatives and stuff to get alpha or integrals to get theta. Behind all of this, we're constantly checking our units. If somebody asks about force, you're supposed to say ding, 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 ding. Force and acceleration are related. We see that happening on a couple of different problems. Then there's the 3 types of acceleration, or excuse me, the 4. We've got angular acceleration, acentripetal, atangential, atotal, and we're constantly struggling to keep them straight. And we're using radians all the time to make sure we don't screw up our conversions. 10.5, let's look at it. Disk, initial rotation rate, omega naught, slows with rate alpha equals k omega squared. K is constant. Determine omega as a function of time. What do you think? How would you attack this one? Am I on the right board, Jules? Thanks. How would you do that? Any ideas?
You take the integral of alpha.
Okay, so tell me how to do it. Tell me what I should write.
Delta W.
Delta
of
omega.
Omega equals the integral of alpha dt.
Okay, and then you plug this in, right? You see a problem.
Oh, there's no T.
There's no t. This integral doesn't make sense. Nice try.
Say like alpha equals,
So that was a good thought. Totally does not work. That's a good first guess though, because that's what worked in the last problem. Huh? What were you going to say?
alpha equals d omega over t,
Oh, what process are you employing now?
separation of variables.
Exactly. When alpha depends on omega, separate before you integrate. Now, strictly speaking here, this isn't quite right. Why? As written, is this going to be positive or negative? This term, k is positive. What is omega squared?
Positive.
So is this going to be positive or negative?
Positive.
So what's happening to omega according to this equation?
It's increasing.
Is that what I said? No, So what do we have to do? Now it's slowing down. Got it? All right. Don't you love? Life is hard. I don't know, but it could be worse, right? We could be having our lights shot off or killed or whatever. We're in here working, so let's try to make the most of it. All right. At this point, then you can separate and integrate. Do you agree? Now you get the omegas with the omegas, the t's with the t's, and you just turn the crank. I know you're tired. Listen to this. I was talking with the Dom and I were up at this conference, what was it, 2 weekends ago or something? And we were talking with the professors up at Cal Poly, and they're like, oh yeah, I always do this problem where they have the separation of variables for a flywheel, and I forget what it was for. It was for the gravitron. Remember the gravitron where the eraser sticks to the edge and they spin it and have it slow down? They were saying, okay, how many revolutions does it complete before it falls down, assuming it slows with this rate? It was the exact same problem, and you had to separate it. So I'm not the only person that's torturing you like this. I know that other teachers at the schools you want to go to torture you like this too. All right, is that enough? We've done all the types of kinematics in 1 hour. Isn't that crazy? We talked about plotting. We talked about taking derivatives. We talked about separation of variables. It's the same old garbage, only now we got to use radians all the time. Okay. I'm fine with stopping class there, or do you guys need any summary? I guess the summary is on page 55. But there's a few little pieces missing there. We didn't talk about the derivatives and such. Well, I think they are in there, actually. Yeah, it's all in there. Should we call that good? You know what? I want to end with one last thing. This is probably a good thing to do. Look at page 58 really quick. I know you're tired. I know you want to go, but this is actually pretty interesting. I have not talked about this yet. You can see where we are going by looking at 10.7. In your workbook, you can see that there's translational quantities and rotational. And today we talked about 3 or 4 of them. And what we're going to do is we're basically going to keep eating this sandwich over and over and over. And next we're going to talk about angular momentum, or instead of mass, we'll talk about moment of inertia. It's page 58 if you want to look. And so that's where we're going. We're basically redoing the first 9 chapters in the next 2 chapters at high speed. Test 3 is tough, but if you practice, you can do it. If you don't practice, it's going to be tough, really tough. But I believe in you. You guys kicked butt today. All right. So